Okay, everyone, good morning. Hopefully you can hear me on Zoom. My name is Jeremiah Bartman. We're really glad to have you here. You're probably seeing a blank screen right now, just because of the way the computer's here. So I'm really pleased to bring in Dr. Stevens from the ARF station out of Sidney, Montana. That's a USDA research facility up there. And we've been really pleased to bring him down to talk about alkaline soil and fertility. And so we got two great presentations today. One on, I think it was ion exchange in the soil or ion battle. And then we'll go into a little bit on precision fertility. So we're going to get started first and talk about the ion battles. Then we'll take a short break and then we'll roll into that second presentation on precision fertility management. So without further ado, I'm going to turn it over to Dr. Stevens. Used to be live, I think, on your mic, but we'll just do a check before we get rolling, and I'll share your screen.
All right. Sound check. Can you hear me online okay? Testing. Okay.
We can see you guys, Jeremiah.
Sounds like we're good. All right. Well, while Jeremiah's getting things going here, let me just tell you how glad I am to be here, to be able to talk to you a little bit today. It's always good to come to Wyoming. Wyoming's home, and I'm glad to have an excuse to come back home. So,
all good, I think. If you have problems, let me know.
All right, thank you. I did try to get a little bit creative with the titles of my presentations. I'm a little hesitant to do that nowadays, to try and be creative or funny, because my wife tells me when I try to be funny, I'm just annoying. So I hope that's not the case here today. But, I'm also glad to kind of be able to talk a little bit about research, something that I don't do as much as I used to. I've taken on a little bit more of an administrative role at our lab in Sidney. And so that takes time away from what I really love to do a little bit. But glad to have this chance to share some of my thoughts with you. A little bit of a disclaimer, I guess, as we get started here. I want to talk a little bit about some of the processes that are involved in how nutrients react in the soil, and make some practical application to that the best I can. And same with the variable rate technology stuff that I'm going to talk about. Not going to get too sciencey, but I'm also not going to go through a list of products that are available and say, this is what you should use and this is what you shouldn't. First of all, there are too many, and they all have a little different properties. But also, that's really not what my role is at USDA, at our research lab. We're looking at things in a little broader sense in our research. But I'm going to try to draw on some research that I've conducted over the years, and some of my colleagues and friends, and hopefully share some information with you that'll be helpful. So glad you're here, and I want this to be, informal. Please speak up if you have comments, questions, and I expect I'll probably learn as much or more from you before the day's over than you do from me. So I hope you learned something from me. All right, so let's get started here. I'm focusing on ions because our fertilizer nutrients are ions when we put them into the soil. So what are they? Well, they're charged particles, plus and minus. This goes back to high school chemistry, where we all remember that with fondness, I'm sure. They can be in solution individually, or they can form structures and crystals when they're in the dry form. And the fact that they have these charges on them is what's important to our discussion today. Some of them are negative, some of them are positive. As you're probably aware, even our soil particles have a charge as well. But primarily, a negative charge, but there are some positive charges in our soils as well. So these undergo different reactions in the soil. Most of what happens wouldn't happen if we didn't have water as a solvent. So water is a critical part of this equation as well. Our mineral fertilizers are salts for the most part. Organic fertilizers may not be to start with, but they become salts. That's how the plants absorb them into the ion form. Now, let's talk a little bit, or just briefly, about chelated fertilizers as well. A chelate is kind of a complex molecule that I'm showing on the bottom right of the screen here that kind of wraps around that salt or that fertilizer ion, which is represented by the red M in the middle. And it kind of forms a little bit of a loose bond so that it can be released fairly readily, but it protects it from some of the other reactions in the soil that we'll talk about in a few minutes. So pH is kind of what we're going to focus on here, and that is definitely an important factor in all of this. All right, so a little bit of a conceptual thing here. I've got on this slide chemical formula for a potential fertilizer. Now, this is not one that we really apply normally. This is not one you could probably buy down at the co-op, but it represents two nutrients that we're interested in: potassium on one side and the phosphate on the other. All right, and we've got our soil here with plants growing on it. So ideally, it'd be nice if we could just put that fertilizer on the soil. It would just, I mean, right now it's in the form that the plant can use it. Put it on the soil. It's gonna just go there and sit and wait till the plant needs it. And when the plant needs it, it's just gonna take it up. Not that simple though. We do have soilless systems, hydroponics, where it does work that way, but the soil is a much more complex environment when we add this fertilizer. So we're going to put that on that soil. Okay, like I mentioned before, the first thing that needs to happen is it needs to interact with water. Can't have any benefit from that fertilizer without the water. Okay, so far so good. It's available. The plant can take it up. And so roots are definitely a part of this equation. They have an impact on these ions. They attract the ions to them. They flow. They attract the water, which brings the nutrients to them. Okay, so far so good. Well, now a little bit of competition. We do have those microorganisms that are in there as well. You know, billions per teaspoon in some soils. They need those nutrients too, so we've got a competition. Okay, that's not necessarily all bad. We get some temporary immobilization from the microbes, but they will eventually release that back to the soil where the plants can get it. All right, now we're getting a little more complex. So we've got things like aluminum and iron in the soil, and they can tie these nutrients up, especially phosphorus and some of the micronutrients in forms that are hard for the plants to get. Okay. We don't have a ton of aluminum and iron in our high pH soils. Much more of a problem in acidic soils, but still can be a little bit of a factor for us. All right, now we're getting more relevant to our soils. Our lime, which is calcium carbonate, and calcium in the soil can interact with phosphorus in particular. So far, potassium is looking pretty good. You know, most of this is kind of focused on the phosphate, but these are the things that we're concerned about. Now, is there anything else? Well, yeah, we've got clay. Anybody got clay in their soil? Well, we're in Wyoming, so you know we got clay. That can have both a positive and a negative effect on our nutrients. Now, if we're talking about potassium, then the clay can hold that potassium in a form that's pretty readily available to plants. It's exchangeable potassium, that's what we call it. It can also fix a little bit of the potassium. Some soils are particularly bad at this, depending on the type of clay that we have. I think most of our clays are pretty forgiving as far as potassium fixation. But it can also bind some of our phosphorus, attract it to the surface of the clay and bind it there. I already mentioned the impact on potassium. Now, the other factor, iron, sodium, calcium, ammonium do have a little bit of an impact on potassium because they're all positively charged. So they're all kind of competing with potassium, competing for sites on the clay mineral and also competing for uptake in the plant root. So if we have a huge excess of some of these, then sometimes that can induce potassium deficiency because potassium just can't get in. Okay, usually not a problem, but can be. All right, let's see if I got anything else on there. Oops, other button. Oh, leaching. We can have a little bit of leaching. Neither of these are particularly mobile in the soil, especially phosphate. It moves just fractions of an inch from where you put it. Potassium moves a little bit better, especially in sandy soils that don't have that cation exchange capacity, so it can be leached out. Generally not a problem with phosphate. So here's kind of the conceptual picture of this ion war scenario that I'm trying to set out. Questions, comments? You probably already know all of it, but kind of want to set things up a little bit. Okay. And Jeremiah, I don't know if there are comments online, if you want to give a shout. Okay. I will try to remember that. All right. All right. Now, one more thing I forgot I had on here. We're talking about pH. So I've got these red hydrogen ions in here as well. That's what pH is how much of that ion is in the soil. In high pH soils, it's very small amounts. In low pH soils, that gets to be a problem. All right, so pH scale, just really quickly. Just a reminder, we go from pH of 0 to 14 on this scale. And when we go from 1 to 2 on that scale, it's not just doubling the amount of acidity in the soil, it's 10 times the amount. So it's a log scale. So actually the amount of acidity goes down, sorry, I got that reversed there, goes down by a factor of 10 for each one. So pH unit is actually quite a lot. All right, so what does that mean in terms of everyday things? I don't want to go over all of these. You've probably seen this pH scale from 0 to 14. Basically, we've got water in the middle, that's neutral. And we've got things on the outside, battery acid and drain cleaner that burn you, and then some variation of in between there. Okay, our soils are generally, in this probably 4 to 10 range, and ideally more in the 6 to 7.5 range. Okay. All right, so let's talk a little bit more about ions and how they impact soil pH and how that impacts crop production. So as I mentioned, when we're measuring pH, we're really measuring the hydrogen ions. Okay, but that affects a whole lot of other ions in the soil. So kind of going from the extreme of an acid soil down to a high pH soil on my screen here from top to bottom. On the lower end, we can have too much iron in the soil. We have a lot of iron in the soil, but it's mostly tied up. But as we get down into pHs below 4, which I would hope we would never be, and I don't expect we would ever be anywhere close to that here in the Bighorn Basin, but if we did, then we would start to see problems with iron toxicity. Okay. A little bit more common, but again, not a problem here, is aluminum in acid soils. And there are some in Wyoming. Go on the other side of the mountain, eastern Montana, some sandy soils. We have some low pHs, so it can be a problem. We have them in eastern Montana. But if we get down below 5.5, then aluminum, which is a constituent of our soils, a lot of aluminum in the soil, it becomes soluble, and aluminum is toxic to plants, especially roots. Here are some barley plants on the top right, looking at the effects of aluminum toxicity on the root system. So on the far right, normal root system, no aluminum toxicity. And as we get farther and farther to the left, we get more and more aluminum damage. So it can have a huge impact. So we don't want to have that problem. That's a bad one. All right. So let's get more into our range at the bottom of this table. Exchangeable calcium and magnesium and primarily calcium are what dominate our soils and determine what our pH is going to be. Now that we can have exchangeable calcium, which is on those clay particles along with the potassium and everything else. And we can also have free calcium carbonate in the soil. We have both. We have quite a bit of calcium carbonate. And that can be a good thing and a bad thing. Calcium carbonate is a base. So it's alkaline, has a high pH. It's also a very good buffer. What that means is that keeps the pH from changing a whole lot. Okay, that can be a good thing too. So, we can have anywhere from a couple of percent to maybe up to 7, 8, 9% calcium carbonate in our soils. I'll talk more about that in just a minute. So I said it's a buffer, so it keeps our soils between 7.3 and 8.5 generally. So for those of you who have looked at a soil test, does that kind of agree with where your soil tests usually fall? Usually in that range. And we're usually closer to 7.8, 8, 8.2. Kind of ring a bell? Okay. All right. So as long as there's calcium carbonate in that soil, it's probably going to be in that range. Now, if we get above 8.5, that indicates a problem that we have too much sodium. And sodium causes sodium carbonate causes a higher pH greater than 8.5. And it leads to soil problems that are kind of a mess. We call them a black soil or a slick soil, slick spot. Just doesn't drain very well, nothing grows. Just kind of a muddy mess. It's similar to some of our alkali spots around here. And in our alkali spots, we have a lot of other salts involved besides just sodium. So we get that white alkali on the top as well. So we don't want to go there either. All right. So let's talk a little bit about how that affects nutrient availability. If you've been to a soil fertility class, you've seen this graph or this chart. The wider the bar on this chart, the more available that nutrient is. So as you can see, most of the widest parts of the bars are between about 6 and 7, 7.5. So when you read about soil pH, that you usually read that that's the ideal range, 6 to 6.5. And that's largely because of this. But you can see that some nutrients become less available at lower pHs, and some nutrients become less available at higher pHs. And if we get into the extremes, then it can cause some real problems. I've also got on this chart a couple down here at the bottom, some microorganisms that are important in nutrient availability. Rhizobia is that bacteria that helps your alfalfa and your dry beans fix nitrogen. So that's an important one. And then we have fungi and some other bacteria as well that help cycle our nutrients. So generally, the fungi are pretty resistant to soil pH. Bacteria don't like the acid pHs. Okay. All right. So with that in mind, let's talk a little bit about some specific nutrients that are important to us and that might be affected by soil pH and some of the reasons for that. So let's start with the big one, nitrogen, our biggest nutrient input. And when it's deficient, it's obvious, right? So why is it so important? Well, it affects just about everything in the plant. It's a component of proteins and chlorophyll. And those are key to everything that goes on in that plant. So how does pH affect nitrogen? Well, it really comes down to that soil microbiome, those microorganisms in the soil that change the form of nitrogen. I mentioned the rhizobium, and we've got bacteria that change your fertilizer N into nitrate if it's urea, or anhydrous ammonia if you have that. Nitrate is the form that plants generally take up, so that's an important one. And if we get too acidic on both of those, then we have problems, but in our high pH soils, it's not a problem. Now we can also have some problems with nitrogen. We can lose it, volatilize it because of denitrification or ammonia volatilization. And that's where our soil pHs being kind of basic can be a little bit of a disadvantage, because especially that enzyme that causes volatilization, or that process of volatilization, proceeds better at higher pHs than it does at lower pHs. The greatest when we get above 10, but really can be pretty active in our normal soil pH range. So the key there is just to protect that urea, if that's what we're using it, incorporate it as quickly as we can into the soil, and make sure that those conditions for volatilization losses don't exist. But once it's in the soil, it doesn't go anywhere. Okay. Questions on nitrogen? Pretty simple, yeah.
Leaching, or what happens?
Well, if I understand your question right, you're asking about pre-plant nitrogen applications, how much to put on, protecting against leaching, or compensating for leaching, or
Yeah, so beginning of the year, you don't have to add.
There are some products available that protect that nitrogen for a period of time. One is a polymer coated product, urea that's just coated in a polymer shell that keeps that urea from reacting with the soil for a time and releases it more slowly over the growing season. That has proven effective, and oftentimes it's blended with regular urea, because if it's all slow release, then you might not have enough early in the growing season. So there's quite a bit of research on different blends, 50-50, 75-25, whatever, on that kind of approach. So that's one thing. Here in the Bighorn Basin, one challenge we have is our dry climate, and we can't rely on Mother Nature to germinate our crop most of the time. So we're irrigating takes a lot of water to do that, to soak up that soil. I think that's where we get a lot of leaching if we have too much nitrogen on pre-plant. So it is a little bit of a challenge. The polymer coated urea is one option. There are also products that we can treat fertilizer with, but are supposed to kind of slow down those reactions and keep it from becoming leachable. And nitrate is the main form that we worry about. When it gets to that nitrate form, it's most easily leachable. We've had for many years a nitrification inhibitor that kind of blocks that bacterial reaction and slows it down. You need to remember about all those things, that they're weather dependent, temperature especially. So the warmer the soils are, the faster that nitrogen is going to become available. So one of our traditional approaches to try to be more efficient with nitrogen in this kind of a situation is to put part of it on pre-plant and live it on and extra fast across the field. But I do think we lose quite a bit with those two plant applications, especially with irrigation. I don't know if I answered your question adequately or not. Anything in particular you had in mind that you're wondering about?
Reduce the amount of passing across the field for the corn and has.
I don't know. Another thing to consider maybe if you put it in a band in a location that maybe is not going to be right under the furrow or something like that, might protect it a little bit from leaching as well. That might be a possibility. Mike?
We're seeing more overhead irrigation and different kinds of irrigation methods. Is it where my mind is going? Can you I'll rephrase the question. So, with more pivots going in, would you consider a greater amount of pre-plant applied nitrogen being safer in the soil and available to the plant versus preferred irrigation, which is that's always been more common with this list. So, can you speak to that?
Sure, good question. I hope everybody online can hear that okay. And the answer to your question is absolutely. With sprinkler irrigation, we can keep that nitrogen where we want it more effectively. Had a colleague in Sidney with Montana State University who did a comparison for irrigation versus sprinkler on nitrogen use efficiency, and they showed pretty clearly that you get more nitrogen into the plant under furrow irrigation, or sorry, sprinkler irrigation than furrow irrigation. So yeah, and in Sidney, we don't usually irrigate up. So that was under a scenario where, first furrow irrigation is after final movement. So you add in, irrigating up, and I would expect to see a benefit. But when you're putting on water with furrow irrigation, you're putting on lots of inches, right, per acre, and maybe even a foot or more with an irrigation. Whereas with sprinkler irrigation, you really can't do that. I mean, you're talking probably less than an inch per application. So yeah, that has a big impact and does protect our nitrogen. Any other questions? All right, let's move along here. The potassium's we can cover this one pretty quickly. Yes, it's important for these reasons that I've listed on the screen. Does pH have an effect on potassium availability? Not really. Some of these other ions can have an impact, especially for adding lime to the soil, which we don't do a whole lot of here, but some. I don't know if anybody's putting on sugar beet lime here, but there's been some interesting in that in some areas. But that can cause a competition problem with some of these other cations like potassium. So relatively unaffected. So let's move along to zinc. Zinc is of the micronutrients. I think zinc is probably the one we need to watch the closest. When I was doing research here at Powell a number of years ago, Mike might remember. You two young guys, maybe not. I think I know you. Tell me who you are. That doesn't mean that. You look familiar. Anyway, we did a micronutrient study and looked at all of the different micronutrients, and the only one that we really saw a response to is zinc. We see that in eastern Montana too, particularly with sugar beets and corn, not so much some of the small grains. Can be a problem with small grains, but dry beans, real important for dry beans. So it's an important one. Does soil pH affect availability of zinc? Absolutely. It will form unavailable compounds at high pH and becomes more available at low pH. can actually become toxic if pH gets too low. So we don't want to go there. But really, zinc's pretty straightforward in my experience. Zinc sulfate's a good fertilizer. It'll increase our soil test zinc levels, and plants will be able to get it. And it'll stay available for quite a long time in the soil. It does react, but really pretty straightforward with zinc. So it's satisfactory, I think, on our high pH soils. We have to watch particularly on sandy soils, lower organic matter soils, or where we have subsoils exposed with zinc, because that's where we tend to see the most severe deficiency symptoms. But we can definitely have some hidden zinc deficiency symptoms if we're not careful. We got to watch that one. Now, what about chelated zincs? They're available. They're good products. The availability is better than something like zinc sulfate, which is just a salt. Pretty expensive, probably not practical on a broadcast basis. One of the advantages of chelates is they work well with liquid systems. They mix well with just running other liquid fertilizers. So, for a starter fertilizer, N-Pro will pop up if you're using a liquid. That's a great option. Okay. Questions on that? Manganese, not a real big issue in my experience. When I was working here in Powell, I did have one of the Western Sugar Field men tell me that they came across a sugar beet field that had some manganese deficiency, and they put a little manganese on and solved the problem. Effective pH similar to zinc, maybe a little bit greater effect than on zinc, tied up by lime. But really, the manganese sulfate works pretty well. Chelated forms are available, but again, pretty expensive. Probably not one you're going to run into. One to be aware of. Questions on that? I'm assuming not. I just clicked right ahead. All right, let's talk about iron in a minute. Not because it's something that we really have to worry about here or we manage, but it's kind of a fascinating case to me. I did some research on it when I was in grad school, and then again at the University of Nebraska in West Central Nebraska. There are certain crops where it can be a problem in certain soil types, and these are can be real high soil pHs, or just typical calcareous soils. You get in soybean country, and particularly in North Dakota and Minnesota, you can have problems with iron deficiency, and this is what it looks like. And in some pretty high pH soils, this is about 8.5 probably, can have problems as well. The interesting thing about iron is that iron's the fourth most abundant element in our soil, in our earth crust, in the soil. So there's lots of it out there. But like I mentioned before, it's so insoluble that plants can't rely on chemistry. So what's fascinating to me is that Mother Nature has adapted. And most of our crops, we just don't see a problem. And that's more so because of the crop and the plant and its characteristics than the soil. Soybeans have developed the ability to respond to low iron situations, and they'll acidify the rooting zone to solubilize that iron, or release organic chelating compounds that they produce to complex it and bring it into the root. Now, that's a genetic thing. Some varieties have it, some don't. So that becomes an issue in those parts of the country where they have problems with that. Same thing with corn. It has a response and everything else. So just because the soil chemistry, that ion war thing is not in our favor, doesn't mean that we're going to have a problem. All right, questions on that? All right, now, this is kind of a big one, so I'm going to spend some time on this one. Let me know if I get too long-winded. I get a little chatty sometimes. I know it's not easy to sit there on those hard chairs for a long time and listen to somebody talk. But anybody concerned about phosphorus high up in this area? Well, going back to the days when I was just a growing up on my dad's farm, and I started becoming interested in learning more about soil science in college. First thing you asked me was, well, what can we do to avoid tying up phosphorus? And I think that, you know, it was certainly a valid question. Was then, it is now. There's no easy answer to it. But boy, it becomes more and more of a question as phosphate fertilizer goes from $500–600 a ton to $1,100 a ton, right? So let's talk a little bit about it. Wish I had a silver bullet, but I don't. Phosphorus is critical to the plant. It's involved in, you know, almost like nitrogen, involved in just about everything, but in a different way. First thing is it's the currency that the plant uses to move energy. You're familiar with a process called photosynthesis. You probably can't see that very well from back there, but here's a chlorophyll, a chloroplast, absorbs light energy, produces a carbohydrate. And it's a complex molecule that has captured that sunlight energy. Okay? We rely on that too. We rely on plants to get that energy from the sun, which is pretty cool, I think. All right, so the plant actually uses that the same way we do to support its growth. It goes through the respiration process, which is the same process we use. So there's a little mitochondria there. The plants have, we have. It transforms that sugar molecule into carbon dioxide and water and energy. And it releases that energy, and then in that process, it shoves it off to a molecule called adenosine triphosphate. That's 3 phosphate ions on it. And those 3 ions are bound together with a real high energy bond. So when one of those is gone, it has the potential to add a third one. Okay? So when there's 2, you can add energy and another phosphate, and you capture that energy. Then that plant can move that around throughout its structure to wherever it needs it, and provide energy to all the other processes in that plant. So without phosphorus, this is why the plant just didn't have that energy. They're kind of stunted, right? If you have phosphorus deficiency, they just don't grow very well. That's part of it. Now, that process also generates heat. Just as an aside, if anybody is a sugar beet grower, when we harvest the beets and put them in a pile, that root's still a living plant, right? And it still respires. And if it respires too much, then it generates too much heat and you get a hot spot, and that's when you start to get rot in the pile, right? So same process. All right, so the other essential role that it has in the genetics of the plant, it's a part of this DNA backbone. So here you can see here the components of DNA, and phosphorus is an important one. And it's here in these side chains here. So that's pretty important as well. All right, so phosphorus impacts root growth. Show that on this image here at the bottom. This is a hydroponic study. Barley, I believe. Roots here on the left where there's adequate phosphorus, and roots on the right where there's not. But there's also a genetic impact here as well. Some plants are more able to survive on lower levels of phosphorus. This one in the middle on the right is not, one that is particularly efficient. So that's a factor as well. All right, so how do we get that phosphorus into the plant? Well, first of all, how much? We're talking quite a bit of phosphorus that our crops remove. Sugar beet, a crop of 30 tons removes about 60 pounds per acre, 205. 3-ton alfalfa crop, 33 pounds, 25 tons of silage corn, about 75 pounds. So, yeah, a little bit. So we do need it or the plant does need it in fairly large amounts. Now, the thing about phosphorus I mentioned before is it doesn't move to the plant. It stays where we put it. So the plant's got to go get it. So the plant really depends on expanding that root system to explore more of the soil profile, or at least get to where the fertilizer is, to get that phosphorus. So anything that restricts root growth is going to also restrict phosphorus. Okay? Compaction, overly wet soils, anything you can think of that's going to impact it. Pruning the root with the cultivator, which is something that I got to be pretty good at. So that's something to keep in mind. And also roots don't grow very well. And then the phosphorus reactions and movement in the soil isn't very fast when the soil is depleted. So when do we typically have the most problems with phosphorus deficiency? Early in the spring, small root system, cool soils. And so that's why starter fertilizer can sometimes be helpful. So a 20-degree decrease in soil temperature will decrease phosphorus up to 0.5. That was pretty big impact. All right, so let's talk about this phosphorus fixing problem. We can divide phosphorus in the soil into 3 different groups. It may look like there's only 2 here, but there's actually 3. The main one is this one that we really don't like. The vast majority is in what we call non-labile forms of fixed forms. That can be largely in our soils inorganic, but our organic matter also contains some of that. And the organic pools are a little more readily available than the inorganic, but they're both considered non-labile, easy for me to say, in general. Now we have some exchange between that group and this group. This is what we call the labile fraction, not necessarily in the water and ready for the plant to pick up, but easily accessible. Okay, that can be both organic and inorganic, primarily inorganic. Now, the one that you probably can't see very well is that little dot. Okay, and that's the form that the plant can actually take up into its root. It's the ion form. So they're in very, very low amounts comparatively. And that's the form that we put the fertilizer on as. So we think of this process of putting it on in this form, it goes up this chain and it gets locked up in here forever. You know, that's kind of our concept of phosphorus fixation, right? Well, it definitely goes in that direction strongly, but it does go in the other direction as well. But I hope to show you a little bit of information that shows that once it gets in this form, it's not necessarily lost. Okay. So why does this happen? I've already kind of talked a little bit about it. We've got different chemical reactions in the soil with those ions, aluminum phosphates and iron phosphates. Not the problem here so much. Calcium, big problem here. And it'll also be attracted to the surfaces of different things in the soil. I'll show you some pictures here in just a minute. Calcium, it's absorbed some phosphorus, and clay can do the same thing as well. All right, so all these things are pretty strongly influenced by soil pH. And this graph, I think, shows this very well. It's very general. Maybe you've seen this before. The soil pH across the bottom of the graph. So neutral soils in the middle, pH 6 to 7, acid to the left, alkaline to the right. All right, so here's that sweet spot, 6 to 7. Now these different lines show how much phosphorus is tied up, the phosphorus fixation in the soil. Okay, and this in general terms, low, medium, high, very high. All right, so you can see where that ideal range of pH comes from. That's where availability is the highest. So you get up into our pH range, around 8, where we see the most calcium fixation, which doesn't look very good when you look at it. That's just the nature of the beast. So, what else do you notice about this graph? Are our soils the worst case scenario? Not even close, right? you get down into these acid soils and, start getting tied up with aluminum, 5.5 pH is really not that acidic. And if you get into the really low levels, we get iron to it. So I guess my message, and I'm going to hit this again, is, yeah, we have some tie up, but it could be worse. That's supposed to make us feel better.
So did they, if I go on by phosphorus, how long does it take from the time you apply it to the time it becomes tied up?
I'm going to get to that. So if I don't get back to that, so the question is about how long it takes. If I don't address it, please call me on it. All right, so let's move on a little bit here. So calcareous soils, we look at them as a bad thing. They have their disadvantages, but also there are some advantages. So looking at that low pH, let me hit on this here for just a minute. I did some of my education in Illinois. So those originally were pretty neutral soils, but didn't have much calcium carbonate in them, as they developed. Started farming them. What do you do when you're growing corn? Lots and lots of nitrogen fertilizer, right? Every year. Unless you're growing soybeans in rotation, then every other year. Every time we put on a nitrogen fertilizer, we're acidifying the soil. You don't see it in the pH because of that calcium carbonate, but every time you put nitrogen fertilizer on, that process of it being nitrified causes an acidified gene. So it's going to neutralize some of that calcium carbonate. It's going to get rid of some of it. In some soils in Montana with lower amounts of calcium carbonate, where we've been doing no-till wheat production, dry land, for years and years, continuously, we're seeing pHs drop, into the fives. So, it can happen. So, what do they do when they start having that pH drop? Apply lime. 5 tons an acre, 10 tons an acre. What's 1%? Okay, if 1% calcium carbonate in our soils, the top 6 inches, which usually weighs about 2 million pounds, 1% of 2 million pounds, about
100,000.
20,000 pounds, right? About 10 pounds per acre calcium carbonate. So if you have 10% calcium carbonate, think of all that lime that's already on the soil that you didn't have to put there. I know, one way to look at it. So most of these calcareous soils are pretty productive. Yeah, pretty nice productive soils here. Well, here we go. Right here with my calculation here. Hopefully I got that right. So it is we do have calcium fixation, and there's really 2 ways that happens. We kind of talked about both of them, precipitation and absorption, and I'm going to tell you a little bit more about that in just a minute. But this kind of gets to your question, Jared, thanks. So what happens when we put that on? This MCP is kind of the most soluble form of phosphorus in the soil. After we put that fertilizer on, it's mono calcium phosphate. And we've got a lot of phosphate for every calcium molecule. Okay, so it's pretty soluble, pretty available. But that phosphorus is going to go down this chain to the less available forms over time. And we'll get to the time scale in just a minute. This is a little less available, so forth and so on. I suspect that we have a lot of this dicalcium phosphate, not super available, but not super tied up either. Depending on our particular soil chemistry, we might get into this calcium phosphate, which is a little less soluble yet. And in some soils, and with enough time, we'll get down into these lower levels, which are very insoluble. This is called hydroxyapatite, the HA there. Just to give you an idea about how soluble that is, your teeth enamel is about 95% apatite. And enamel, it does erode over time, but really slowly, right? So that's pretty unavailable. And chances are, we don't get a lot of that developed in our soils, but it is one form that it can get to. Now, the last one on here is fluoroapatite. So that's appetite with fluoride added. So what happens when you brush your teeth with fluoride toothpaste? Your enamel gets even harder. Okay. So those are the species we're looking at. So this represents a fertilizer molecule. I say map here, probably really should be a calcium phosphate from the source that I got this from. So we have that, we put it in the soil, and we have our calcium minerals in the soil. We get water in that. So that starts dissolving that fertilizer material, which is water soluble. And then it starts, we also have some other minerals in the soil around that particle. We develop phosphoric acid inside that granule, which again is very soluble and acidic. So that's going to then move out into the soil around it, react with chemicals and the calcium, going to dissolve a little bit of those calcium minerals, releasing that calcium so it can tie up the phosphorus. Okay, the first product that we get though, as I mentioned a minute ago, is this dicalcium phosphate, which is relatively available. And it's not going to move very far from that fertilizer particle, like I mentioned, because it just isn't mobile in the soil. So we get this little halo of calcium phosphate around that fertilizer particle. Again, mostly available. Plant can get to that pretty well. This is what it looks like in real life. Fertilizer particle about 3/16 of an inch in diameter. And as that phosphorus moves out and diffuses just another few 16ths of an inch, and it starts reacting with that calcium and forming calcium. So that's what's happening in the soil when you put a dry fertilizer on there. Liquid reacts similar, only it's just a little different physically, liquid versus a particle. All right, so let's talk about some of our traditional concepts and kind of getting to this timing question then. So in the first few weeks after we put that fertilizer on, again, we go to that fairly available monocalcium phosphate, and then some of these that are a little less available, but the plant can still get to it. Okay, out 3 to 5 months, we might get some of this less available material forming, and even longer forms, longer times, it's just going to continue to become a little less available. Long periods of time, we might get some hydroxyapatite. Again, if our soil chemistry is favorable for that. So it does kind of progress over that kind of a time scale. So within a year's time, we're talking pretty good availability. But starting in a matter of weeks, it's going downhill. And certainly in a few months, we're going to see significant decreases, like maybe up to 50% reduction in availability. Yeah.
Typically, we fertilize our alfalfa fields in the fall.
Uh-huh.
So the fertilizer has time to break down and be usable for the plants.
Yep.
Is that the wrong thing to do then if it's starting to get tied up in the soil?
I would say no for a couple of reasons. And I'll touch on some of this a little bit later as well. But two things: when you're putting it on alfalfa, you're putting it on the soil surface. So it does need a little bit of time just to get some moisture on it and get it into the soil, right? Keep in mind, it's not going to go very deep, but deep enough to get to the root. So that, I think it's beneficial to put it on in the fall for that reason. Also, soil temperatures are getting a lot cooler in the fall, and they will eventually freeze up, right? So those cooler soil temperatures are going to really slow down these fixation reactions as well. And so I think as long as that soil is frozen, I think we're kind of keeping it at a steady state until it ends up. So again, we'll touch on this again in just a minute. One of the core principles of fertilizer management is putting it on at the right time, which means closest to when the plant's going to use it, which would suggest spring is better. But again, we've got to get it into the soil, that top dress application. So kind of a toss up in spring and fall, but I think the reasoning is sound and valid. Make sense? All right. So these are the numbers that scare us. Fertilizer recovery. First growing season of that fertilizer phosphorus we put on the soil, we get maybe 30% in it. $1,100 a ton, and only getting 30% of that, right? That's the scary number. But keep in mind, that's just in the first growing season. We're kind of feeding that reservoir, that big, huge reservoir of phosphorus. Some of it will come back. Probably not all of it. You know, over years, maybe 10 years, you know, we might get 80% of that back. That's just kind of some rough rule of thumb figures, but it is a reversible reaction. All right, so we talked about precipitation of phosphorus with calcium. This is what happens with calcite or calcium carbonate. This is an electron micrograph of calcium carbonate crystals with exposed to 0 phosphorus. It's nice, clean, beautiful looking crystals. Okay, just equilibrated with water for 10 days. Okay, if we add some phosphorus to that, 50 parts per million, here we still have those calcium carbonate crystals, but we're starting to see some of the phosphorus get attracted to and down to that calcium. So that does happen, just part of the process. So there is a little bit of a paradox. You know, we talked about fixation. I think we kind of beat that to death. Now, I kind of want to talk a little bit about what some of our options are. Let's see here. As I mentioned, plants and microorganisms have adapted mechanisms to help with this process. We'll talk about a couple of those. And of course, this becomes more of a concern when our prices are the way they are now. So, basic principles of nutrient management. You've probably heard this before. If not, well, here it is. The 4 R's of nutrient management. And these are principles that we hope will improve our fertilizer use efficiency. Okay, so it means the 4 R's, you know, have certainly environmental impacts. Phosphorus can be a pollutant, economic, obviously, for our production systems, and social impacts as well. So what are the 4 R's? The right rate, the right placement, the right source, and the right time. Okay. Probably not me to say anything. And we're going to talk about some of these things as we go along. All right, so let's start with the first one, the right rate. How do you know how much to put on? Good answer. I wish I had some candy. I'd throw some candy at you. Okay. Well, the answer is soil test. And the question was, well, you heard my question. All right, so that is certainly the first tool in our toolbox. That's part of the equation. So yeah, let's talk about soil testing. You knew I was going to have a slide in there, didn't you? All right, so as with a lot of the things that we manage in life, it makes it a lot easier to manage it if we can measure it and we know it's there. Sometimes it can be a little difficult to understand what a soil test is telling you. Agree? Yes? Disagree? No? Me too. But we have to understand some things about what a soil test is. It's an index. With nitrogen, we can measure the amount of nitrate in the soil. We know that's all available to the plant. Okay, so that's a pretty definite measurement. The phosphorus, it's not quite so easy. Well, nitrogen is not either, because there's a lot of other things going on with nitrogen. But that particular test is pretty straightforward. So we develop procedures to give us some numbers that we then correlate with how a plant responds to added fertilizer. So that's kind of what a phosphorus soil test is for us. And it kind of tells us what the probability of response is. So if we have a soil test level that's very low, we can be pretty sure that if we put some fertilizer on, we're going to see that benefit immediately. Okay, if our soil test is medium or high, we might not see it that year. Okay? Might be fertilizing the system for next year. Anyway, or we may not need to put anything on it, which is most likely what we should do. All right, so some different philosophies to handling soil testing and interpretation of soil test results. The one that we generally focus on in the Western United States is just making sure that the plant has enough to reach its potential. Maximum yield, maximum economic yield, whatever the case may be. I'll talk more about that in a minute. It's not a perfect tool, but it is a pretty good tool. Okay, so you need to become familiar with soil tests and use them, particularly when fertilizer prices are sky high. If you've got it in the soil, why buy more and put it in, right? All right, so soil test phosphorus is just one factor that affects our plant response. That's why sometimes your soil test will say you're going to get a response, but you don't. So there's a lot of other things going on, soil physical conditions, weather, what crop you're growing. We'll talk a little bit about that, and maybe we have some phosphorus deeper in the soil. Okay. All right, so let's dive into this a little bit here. So if we as soil fertility people do field research to determine how much phosphorus we should apply in a given situation, we pick a site that has a particular soil test level, put on different levels of phosphorus fertilizer, and we measure the yield at those different levels of phosphorus fertilizer. We get this yield response curve. Okay, seen one before? Yeah. All right. They don't usually look this pretty. I made this one from fake numbers. Sorry. But this is a couple of points I want to illustrate here. I mean, yeah, we'd expect it when we put on zero fertilizer that we wouldn't get as much yield. Now we'll never, I don't think, ever get zero yield or zero phosphorus. Okay, so we're going to start up here somewhere. Okay, so we put on 0 pounds, we get 38% of our yield, or 38 bushels, or whatever you want to put on the scale. Okay. All right. So then let's go to another level. Let's go to 60 pounds per acre. Okay, we got a response. Soil test was low, so we were going to have a pretty good chance of a response. We did get a response. So we go from 38 to 70 something. Okay, pretty big jump, right? All right. So this is where we start thinking about economics. How much did it cost me to buy that 60 units? And how much did return did it produce? Right? Basic economics that you think about every day, I'm sure. All right. So as we go up this curve, I put on 120 pounds. They were up to 90 plus, but we didn't get as much bang for our buck with that same input cost as we did with the first one. And that's just a general basic principle for this kind of response, yield response rate. Okay, now let's go up here to the top of the curve. We always want to have the best yield in the valley, right? How much are we willing to spend for that, right? So we put on that next 60 unit application, and if this is percent, then I'm doing really well. So I'm going to do about 103%. But the point is, much less return. So what is the value of that crop that you're producing, and is that input cost justifying what you're getting out of it? Right, make sense? All right. So let's put some real numbers on it from Powell here. Mike helped me I helped Mike with this study a few years ago, sugar beet study where we did some different phosphorus treatments. So I'm going to share a little bit of those results with you. This is the yield curve from one of the years, 2013, out at the research station. These are the characteristics of that soil or that site that we put it on. pH of 8, organic matter 1.5, 7.4% calcium carbonate. So we're up there. And soil test phosphorus is 14 parts per million. Now, one of the problems with doing phosphorus research on a research farm is that researchers don't like to have nutrients be a limiting factor when they're doing variety trials or other kinds of research. So it's hard to find a spot on a research farm where we have real low phosphorus. This would be a medium soil test level. Really, in the 5 to 10 parts per million range is where we really expect a response. So we're above that. We did get a little bit of a response as we went from 0 to way up to 300 pounds of phosphorus per acre. You would not do that, I don't think, especially at $1,000 an acre or $1,000 a ton monoammonium phosphate, which is what these numbers represent. So as we went from 0 to 30 pounds, we got a pretty good bump. Kind of like our yield curve on the previous slide would suggest, the biggest increase of all of them. We did continue to get increases all the way up to about 180 pounds per acre. But, just throwing out a number for the value of a sugar beet crop, I'm going to say 50 pounds or $50 per ton, roughly. I think I'm close. And so we're putting on, for every 30 units of phosphate, it's costing us $30. So that one pencils out. Put in $30, get back 50. You just have to go to 60 and with these prices, no one seems to. Okay. Certainly don't want to be up at around 100. Right? All right. So same concept, different year, same study, 2014. Again, we fit a curve to it, but you could almost say we got a good bump with that 30 pounds, and then it was pretty flat after that. Right. Pretty simple colors and sense there. All right. So what can we do? Next item on our list of placement. So we talked a little bit about that. We have some options. We can do broadcast incorporated, which is our normal procedure. Put it out there, work it in. That has its advantages. You've got that phosphorus distributed throughout the soil profile. Roots can grow through the soil and get to that phosphorus pretty easily. However, that's the maximum exposure of that phosphorus fertilizer to those ion reactions in the soil, right? No protection unless we have some kind of product that we can add with it that might help. We'll talk a little bit about that. So we can band it. That puts it in a concentrated form, less exposure to the soil. So preserves that availability for a longer period. Okay. And typically, we can get the same benefit from less phosphorus if it's banded than if we broadcast it. How much could you reduce your phosphorus rate? So that's a matter of opinion. Some people say up to 50%. I'm a little nervous about that number. I think 20 to 30% is probably pretty safe. We could reduce our rates because of banding. Yeah. So banding is an option. How about in furrow as a pop-up? Some of the wheat growers do that quite a bit. Put a little bit of phosphorus in with the seed on the dryland farms, especially. Haven't done that so much under irrigation, but there are some people doing some things with in furrow stuff, particularly in Red River Valley for corn and sugar beets. Put a little liquid phosphorus in furrow and nothing else. They'll fertilize their rotation crops regularly with phosphorus, but just put it in furrow for the beets and the corn. So that's an option. It has its risks and its benefits. Risks being that anytime you put salt in the seed, you're risking seedling injury. Okay. All right. Top dress. The alfalfa situation that you raised, we're just putting it on the top. We're not incorporating advantages and disadvantages. Right? And then variable rate. Oops, there's a typo there. I thought I got all those. Sorry about that. I always find one when I stand up here and do a slideshow. So that's putting it in the right location in the field, hopefully. We'll talk about that again in a few minutes. All right, let's talk a little bit about banding and when we might expect to see a benefit. There are really two scenarios where we would expect to see the biggest benefit. And the first is illustrated here from my one of the scientists I worked with in Illinois, Bob Biff, shows that a yield increase from fertilizer. Again, this soil test level, don't expect to see a big increase out here. More as we get to the lower soil test levels. With broadcast, we're going to see a benefit. But as we get into these real low levels, that's where we would expect to see more of a benefit from the banding. Again, preserving its availability a little bit. Now, the other scenario where we see more of a benefit from banding than broadcast would be in a no-till situation. Again, in Illinois, we did some work with corn. Didn't really see a big benefit from starter fertilizer in full tillage, but in no-till we did. Cool soils, roots don't grow as quickly, and it's harder to get the fertilizer where you want it to. So a couple of scenarios where banding would be particularly helpful. All right, so in this study that Mike did, that I helped out with, we compared some of these things. APP is a liquid phosphorus, ammonium polyphosphate. We did that alone and with an availability enhancer that you probably heard of, Avail. Now, the concept behind Avail, as I understand it, is that it kind of diffuses out into the soil ahead of the phosphorus and reacts with the calcium before the phosphorus gets to it. So it kind of prevents the calcium from doing its damage for time. Okay, so conceptually, it has some advantages. Then we also put some impearl in with that treatment as well. And then we did broadcast of 1152 with and without Avail. So in 2013, our pop-up treatment really did well. Lower yields that year, weather wasn't great. So lower yields overall. So having that readily available during those conditions. Didn't see much benefit from the Avail in either circumstance. There's a numerical difference there, but statistically, that's a pretty small difference. So that was 2013, 2014, same treatments. And in this year, we saw an advantage to the banded fertilizer. It also happened to be the liquid. I don't know if it was because it was liquid wood or because it was banded, but it did a little bit better than the broadcast with that. But probably a combination of both. I suspect the placement was probably the driving force there. This year, the pop-up didn't really provide any additional advantage. I know in at least 1 year, we did see a little stand reduction from the pop-up. So that is a risk. All right, so a little bit of indication here that at least with the map, that Avail might have helped a little bit. Not statistically significant, but close. If we loosened up our criteria a little bit, we might be able to say it's significant. Okay. Questions on that?
Thank you. So Bart, certainly with my interest in seed production, our grass seed producers, especially on Heart Mountain, and those soils really calcareous. And most of those guys say a soil test is never going to show them that they need any phosphorus. And yet they're putting down 100 units, pretty regularly, maybe not every year, but every other year. And they say they see a response. It's not Bart Stevens with his plots, but I have to believe they're not putting it on without some return on investment. So with that in mind, as well as some recent work by Allied Seed, they've been working with OFOS for alfalfa seed production especially, but it certainly piques my interest that OFOS might work with other crops, and they're putting it on as a foliar feed fairly late in the growing season. And they're seeing significant yield increases. And I believe what they're putting a lot of that yield increase to is increased seed size. It's going on late enough in the year that it's not probably, affecting seed set, but it is affecting seed size. And I believe they believe it's in fact affecting maturity. So you have some of those later florets that were pollinated that are actually make seed successfully. So can you speak to, and maybe also just a foliar feeding with phosphorus and its availability maybe throughout the growing season as well?
There's a lot in that question, Mike. Good question. Thanks. Short answer, and I kind of hope to make this my final point, but I'll make it now and then emphasize it again later. There's so many different options out there for products and different ways to handle our fertility that it's really impossible to do a good job of evaluating them all in a research setting, as you suggested. So I'm a big believer in, if you think something might work, try it. And if it looks like it works on your farm, keep doing it. So I think that's a huge part of this equation. But as a scientist, I'm going to touch on it the last, but it should probably be more of a focus. I'd be okay with that. The other part of your question, foliars. As part of that micronutrient study that I did, we did put on some foliar treatments. And yeah, the plants take it up. If you put it on foliarly, it gets it into the plant. So it's an effective way to put on a little bit of fertilizer. And if the plant is in a high demand situation where it just can't get enough to fill out the seed or set seed or whatever the case may be, it may be a benefit. Don't have any research data to back it up. Don't have any research data to say, no, it doesn't work. You can probably find some out there to support either sides of that argument. But yeah, if it works on the farm, sure. Yep. All right, we're getting close. How far over my time am I, Jeremiah? All right, the next one's a little shorter. Oh, man, you guys want to take a break? Okay. I'm close. Source, kind of touched on that already. We got dry, whoops. Button. I think I got it back. We got dry fertilizer, liquid fertilizers. Manure is a great source of many nutrients, a little harder to manage. Availability enhancers, a lot of those out there as well. I've talked about one. With high fertilizer prices, a lot of interest in some of these products. Biologicals, we've got different kinds, inoculants, biological stimulators, ranging from extracts from like manure and kelp that have a lot of different organic compounds to growth regulators that help stimulate root growth. And that there may be situations where any of these could be a benefit. Haven't done a lot of research with them. I'm gonna try one this summer in a study, and it'll be interesting to see how those things work. But again, can't share a lot of data with you on that, but try it on farm. See if it works. All right, timing. I already talked about this a little bit. We're going to put it on in the fall and the spring, every year, every 2 years, every 3 years. These are all questions that are valid questions. And as a rule of thumb, as I mentioned before, put it on as close to when the plant needs it as we can. But economics are a part of this as well. That has to be a huge part, saving trips across the field. All right, so just a little bit of data here from a really old study from Colorado. Really good study though, kind of looking at this very thing in a new alfalfa stand. Goes way back, like I said, 1976, but the principles still apply. So the crop was seeded in 1976, and they did soil test and yield collection here over the next 6 years. These are the characteristics of that soil. This one was in western Colorado, high pH, low organic matter, high calcium carbonate. Now, both of these soils have a pretty high soil test phosphorus. 26 parts per million, is pretty high. You wouldn't necessarily expect a response. But this is looking at what happens to that soil test level over those 6 years with 5 different approaches. Okay, this is where we started. Okay, so let's start with doing nothing. Okay, don't put any phosphorus on it at all. That soil test level drops pretty precipitously over that time. Gets down in close to that range, 10 parts per million, where we'd be concerned. So we can draw it down and draw it down fairly quickly. First couple of years, we're still in pretty good shape. All right, well, what if we put a little bit on every year? 50 pounds a year? We keep it up there and maintain that pretty well, if not increase it a little bit with 50 pounds. Well, what if 50 pounds is too much? You can't afford it. 25 pounds, you really didn't cut it. Not as bad as 0, but it does continue to drop. All right, so what about putting a bunch on it at seeding, plowing it down? Okay, we do that quite a bit. Been recommended to do that for quite a few years, put on 2 or 3 years worth. So they put on 75 pounds. No, sorry, this is kilograms per acre. So I think this is more like 20, 40, and 60 pounds. So we put on 60 pounds first year at seeding. Didn't do anything for 3 years. Well, let's take 2 different scenarios here. Didn't do anything after that for 6 years. And we did pretty good for the first 3, maybe even 4 years. And then we dropped off. And then if we added another shot after 3 years, bump it back up. It's kind of like you did. So what's best? Comes down to an economic question, I think. Certainly from an efficiency standpoint, putting a little bit on every year makes some sense. From an economic standpoint, maybe every 2 or 3 years makes sense too. So again, I think that's something that each grower kind of has to figure out on their own. Another soil type kind of shows the same thing, so I'm just going to skip over that one. So a couple of final thoughts. So our soil pH is something we definitely need to be aware of and how it influences our nutrients and their availability. But it could be worse. We could be on low pH. Fertilizer P is fixed in our high pH soils, but we do get some of that back. And fertilizing from max net return is probably pretty wise right now instead of maximizing yield. And then just keeping in mind those 4 R's as you make some of those decisions. Kind of looking at the nutrient package as a whole. Let's see, what do I say there? If our soil tests are in that medium to high range, then on a short-term basis, when costs are high, we'll probably cut back a little bit and save some money and not hurt. Oh, I did want to go back on that phosphorus study. Didn't really have a whole lot of impact on yield. Anyways, it's kind of crazy. Now, part of that I think is because they took a 1 foot soil sample, and really all the action of phosphorus is in the top few inches. So they might have been diluting some of that. Might have had more phosphorus available than this is showing. But also, once you get an established fertilizer alfalfa stand, you got that extensive root system, and it's getting every bit of phosphorus that it can. That helps us too. All right, so back to this. You've got to keep economics as part of the process, part of the equation. Talk about banding. It can be beneficial in certain circumstances, and timing. And then finally, back to Mike's question, try some things out on the farm, see if it works. No, that's hard to do. hard to take a strip and just do something different on one strip. It can provide some pretty useful information. All right. Sorry for talking so much. Actually, this is a little misleading. I think we're more like here. So and make you a little feel a little better, I hope.
So over those years when the phosphorus becomes available again, that's just all natural processes, or is it a combination of putting more fertilizer on or different fertilizers or something, some kind of additive to help break that apart faster?
Well, I think in that situation that I described, it's natural. Whether or not there are products that we can add to speed that up, I guess is a matter of debate in the research community, has been for years. They've looked at microorganisms that are supposed to be able to release some of that phosphorus, seen some benefit from that in some parts of the world. Haven't really shown a lot of benefit here in the United States. That's kind of old research, a lot of new products now, hard to say. But I think most of the products that we're looking at now really are focusing on that root zone, either increasing the root zone, enhancing root growth, and protecting that phosphorus fertilizer rather than mineralizing and releasing what's already there, in my understanding. Somebody from the fertilizer industry could probably correct me on that. But I'd say primarily natural processing.
Okay, great. Thank you very much. We'll take a we'll just take a 5-minute break here, and we'll switch presentations and go from there.